In this video, we're going to introduce chemical equilibrium. Now, when you think about the word equilibrium, if you've had your general physics course at this point, then you already have a general understanding of what this word equilibrium means, right? You've probably dealt with the concept of mechanical equilibrium in those general physics courses, where the forces acting in one direction are equal to the forces acting in another direction. And so you achieve a mechanical equilibrium where the net force that's acting on your object is going to be zero. The idea here in chemical equilibrium is similar, but applied to chemical reactions. And so first, in order to understand chemical equilibrium, we have to discuss the concept of reversible reactions, right? So at this point, we've talked about a lot of chemical reactions where we have some product, some reactant A forming some product B. And typically we draw this arrow going in one direction, saying we're going from our reactants to our products. This is what's known as an irreversible reaction. Right? Basically saying that, you're forming your products and that's it, right? It is irreversible. It's only going in one direction from A to B. But what happens if you can actually reform your original reactant? What if B can actually form A? That actually happens in a lot of chemical reactions, and that's what we call reversible reactions. And we denote them using this double-headed arrow. So we have one arrow going to B, but then another arrow going from B to A. This is known as a reversible reaction. And so this double-headed arrow implies that you can not only form B, but B can turn back around and form A as well, right? So this is analogous to the forces acting in opposite directions that I just talked about with mechanical equilibrium, right? You've got two things going in two different directions. Now, when we're talking about an irreversible reaction, we know that the reaction has stopped when we're either out of A or we're not forming any more of B, right? For a reversible reaction, we know that the reaction has stopped when it reaches equilibrium. And equilibrium is just a point where no more of A or B is being formed. Right? So where you've got equal concentrations of A and B. So let's look at an example of a reversible process, right? So if you take NO2, right? So NO2 gas can dimerize and form N2O4. Right? So if we're balancing this guy, then we got to put 2 there, right? So NO2 can dimerize and form N2O4, but just as likely N2O4 can decompose and form 2 units of NO2. So this is a classic example of a reversible reaction. NO2 forms a dimer by bonding at that central nitrogen and forms N2O4, but also N2O4 can break apart to form NO2. So when do we know it's reached equilibrium? So let's look at a plot here. So let's say we draw out a plot, and on the y-axis, I'm just going to have the concentration of our substance, right? So the concentration of whatever our substance is. And on the x-axis, I'll have time, all right? So this is time as the reaction progresses. And this first curve I'm going to have will be for NO2. So let's say we start with a vessel of NO2. Right? So just kind of drawing out this plot here. In fact, let me redraw that. That's something like this. Give myself enough of a straight line region. Okay, so this will be our plot for the concentration of NO2. Right? We're starting with a vessel of NO2. It starts to decrease as the reaction proceeds. Simultaneously, we'll have N2O4 that's being produced as well, right? Right, so N2O4, concentration here as well. Now, this point in time where there's no more, where the concentration of N2O4 and the concentration of NO2 is constant, this is your region of equilibrium. Right. So that's what I mean by, there's no longer any change in concentration of N2O4 and no longer any change in concentration in NO2. Now, one thing that I want to kind of clear up from the beginning, and that I think a lot of students get confused with, just because these concentrations are no longer changing, that does not mean that this reaction has stopped. That doesn't mean everything has stopped. Equilibrium does not imply a static process. So I'll say it's not a static process. Equilibrium is a dynamic process, right? So there's still activity going on. So equilibrium is a dynamic process. Right. So there's still stuff going on at the molecular level, right? There's still N2O4 being produced. There's still NO2 being produced, but it's just not, it's to a point where the concentrations remain consistent. So the analogy that's usually used here is cars traveling on different sides of a highway, right? If it's during a particular time where people are leaving the city or particularly prone to coming into the city, then you will have drastic changes in the number of people that are in or out of the city. But if it's a relatively stable time, right, where there's an even number of people going in and out of the city, then you don't really change the population of the city, but there's still this dynamic process of cars coming and going, but it's not changing the concentration of people in the city. Same thing with equilibrium processes, right? There's still reactions going on. There's still stuff being formed, stuff being decomposed, but it's not enough to actually change the concentrations of the reaction. It's reached a point where the chemical reaction is stable. The concentrations are stable. So I don't want you to think that because these concentrations are changing, are not changing, everything's just grinded to a halt. These reactions are still going on. It's still a very dynamic process, but at this point, the concentrations are not going to change. Okay, so that's a general introduction to equilibrium. So now the rest of this unit will focus on how do we quantify equilibrium, right? How do we show which side the equilibrium favors? Will it produce more N2O4 in this case, or will it produce more NO2? Where does it sit stable, right? Trying to quantify these equilibrium processes is tricky, but it's something that's very foundational to understanding equilibrium. So we'll talk a lot about how we quantify it and how we further understand these equilibrium processes.